Okay, so we're going to continue with looking at other fun things that Laplace transformations can do for us. So this time we're going to define derivatives. So how does it look when we try to take the derivative of a transformation? And so you can kind of see the process there that our form has to be a function of t times n times f of t. And then the nth derivative would be negative 1 to the nth, that nth derivative of the given particular f transformation. So let's take a look at an example. So as with anything where we're trying to mirror a particular form, we do want to take a moment at the start of the problem and identify the characteristics that map onto the appropriate pieces. So for example, I need to know what n is. So n comes right here, and that's useful for the derivative piece. So I'm looking at the exponent of t, and so I'll make a note that n equals 1 in this case. I should probably figure out what f of t is. So that piece right there, because that's going to correspond to the appropriate transform. So in this case, f of t would be sine of kt, and so the appropriate transform there would be k over s squared plus k squared. So let's put all those pieces together then. So t sine of kt would be negative d ds of k over s squared plus k squared. And so then we just need to apply the appropriate derivative on that. So I'm going to rewrite this d ds, so k times s squared plus k squared to the negative 1. And I'm a little off screen there. Let me move that up. Okay, so because I'm taking a derivative with respect to s, it means I can treat the k's as constants. So that k is going to stay out front. Bring down the negative 1. So that's s squared plus k squared to the negative 2 power. And then chain rule puts a 2s there. Okay, and so let's clean that up. Negative negative makes it a positive, so we have a 2ks up top, and then s squared plus k squared squared. Alright, so you might need to refer back to a couple lessons ago where we looked at Laplace transforms with initial conditions and how that process worked, in case you're drawing a little blank, like, well, where to get this stuff? Okay, so the initial part is I'm going to take the Laplace transform of each term, and there's different rules about the types of derivatives that we're dealing with. So I want to take the Laplace transform of the second derivative plus 16 times the Laplace transform of x and the Laplace transform of cosine of 4t. Alright, and how does that process work? Well, Laplace transform for the second derivative has, so it's got s squared, and then it's a function of x in terms of s, minus s x of 0, minus x prime of 0, and then plus 16 times x of s, And then the Laplace for cosine of 4t is just s over s squared plus 16. Okay, then we can plug in our initial conditions here. So x of 0, that's just 0, and that piece is just 1. So I want to try to get, trying to solve for x of s. So that's s squared plus 16 times that s of x function. And we'll bring the 1 over. Alright, so I'm still trying to isolate x of s. So it's going to be 1 over s squared plus 16 plus s over s squared plus 16 squared. Alright, so then I want to do the Laplace transform, or the inverse Laplace. Of each term. And this is where I'm going to remind us of a pattern we just learned. Okay, so we actually just saw, let's kind of do the side quick reminder here. So we just saw this pattern for t sine of kt, which was the inverse Laplace of 2ks over s squared plus k squared squared, which fits this term pretty well. So we just have to have that conversation of, well, what is k in this case? So k is 4. So basically I need a 4 in the numerator, so I can't just put a 4 there. So I'm going to put a 4 there, and I'm going to divide by 4 on the outside. And then for that t sine of kt term, I need that to say 8 in order to properly fit that pattern. So if I put an 8 there, that'll put a 1/8 out there. And then what are we looking at? Well, we are looking at 1/4 sine of 4t and 1/8 t sine of 4t. Alright, I think it's time for a new definition. So convolution. So what is a convolution? So if f and g are piecewise continuous functions on the interval from 0 to infinity, then the convolution of f and g are denoted by this symbol. F star g is a function defined by the integral that's given on the screen. So integral from 0 to t of f of tau times g of t minus tau d tau. That t looking symbol. Anyways, it's just another letter of the Greek alphabet, so don't get too excited or nervous about that. I don't know why. I felt like when I was going through that last bit, I'm like, you know, I remember being in math classes and my teacher having to show me that other letters of the Greek alphabet exist, and we just don't talk about some of the more interesting ones, I guess. So I just thought I'd take 30 seconds and just put a brief Latin alphabet or Greek alphabet up on the screen. Some of these we're pretty familiar with, like alpha, beta, gamma, delta, epsilon, zeta, maybe not, eta, theta. With theta we know. Iota, kappa, lambda. Okay, so some of those we've seen in classes. Omicron, pi is pretty common. There's the tau one, and so there's an upper and lower case for these things. Epsilon, Okay, so I don't know. I don't know if you needed to see that there's other letters out there, but in the middle of me talking, I just went, oh, that'd be nice to kind of show.